During the last many classes, we were essentially studying the operation of all the three kinds of laser, namely the gas lasers, liquid lasers, and solid state lasers. To this end, we essentially selected some representative lasers from each category and studied them in rather detail. For example, in case of gas lasers, which again can be categorized into three types, that is atomic gas lasers, ionic gas lasers, and molecular gas lasers. Molecular gas lasers. For atomic gas lasers, we chose helium neon laser as a representative laser and studied its working in rather detail. For ionic gas lasers, we on the other hand chose argon ion as the laser whose operation we studied. Argon ion is of course one of the most important and popular laser of this category. However, for understanding the operation of molecular gas lasers, it is essential to have a basic understanding of molecular spectroscopy. Therefore, it has been decided that molecular gas lasers will be undertaken at a later date, later time during this course. For liquid lasers, we chose dye laser, which is the most important liquid lasers, and try to understand the mechanism for which the liquid lasers offer continuous tunable operation. It gives continuous tunable emission. For solid state laser, we chose the most popular solid state laser, NDL, which of course provides coherent light at discrete wavelength. However, there is yet another type of solid state lasers which provides continuously tunable output, tunable emission, much like dye lasers. However, the continuous tunability occurs over a much wider range of wavelength spectral region as compared to dye laser. And for this category, we chose operation of titanium sapphire laser, which provides tunability over a very wide range spectral region, starting from almost red end of the visible, and goes down to deep in the infrared, or even more than 1100 nanometer. Quite wide tunability. Red end of the visible is about 680 nanometers. So the tunability is from 680 nanometer to almost 1100 nanometer. So having completed these three categories of laser, of course, molecular gas laser is still remaining. We will come to that, as I said, very soon. We now in a position to turn our attention to the few specific and important type of lasers which cannot be categorized into any of these three types, that is gas, liquid, or solid. One very important such laser is Excimer, which is very important because it provides continuously tunable coherent continuously tunable coherent, extremely sorry, not continuously. It provides coherent light at UV region of the electromagnetic spectrum, the ultraviolet wavelengths. Before we try to understand the working of Excimer laser, let me very quickly tell you what is the importance of coherent light at ultraviolet frequency, ultraviolet wavelength. You see, from the theory of diffraction, which we have studied in quite detail when we spend some time and understanding the behavior of light, we have seen that when a beam of light strikes an object, it undergoes natural diffraction limited divergence that reduces with wavelength of light. That means when a beam of light strikes an object, which could be an aperture, which could be an opaque material, then the light bends around its edges due to diffraction. And this angle of bending is proportional to the wavelength of light. That means longer is the wavelength, more would be the bending. So then, what is the consequence of that? Consequently, a laser beam of shorter wavelength can be focused by a lens to narrower spot size. So, the spot size, because the bending increases with wavelength. So, if the wavelength is shorter, then it can be focused by a lens to a narrower spot size. The spot size will thus be larger for red light than for green light, which will again be larger than the blue light. So we have chosen three examples. One is the red light, green light, and blue light. And if we focus these three beams by the lens of same focal length, then if there are no dispersion, then if you would focus a beam of light, if there are no diffraction, if you would focus a parallel beam of light, it will be focused to a point, provided there is no diffraction. But in reality, there will be diffraction, and so when you focus, it will not be focused at a point. Instead, it will be, there will be a spot size of the beam at the focal plane. So this is the focal plane. So if its focal length is f, so this is f. So at the focal plane, it will not be focused to a point, but there will be a focal spot of diameter, say d. So if you have red light, then the focal spot diameter will be more than if you have a green light, because the wavelength of red, wavelength of green, and wavelength of blue, wavelength of red is more than wavelength of green, more than wavelength of blue. So the focal spot size also will be, if we call it dr for red light, dg for green light, and dB, that is the diameter of the focal spot for blue light, then dr would be more than d green, which will be again more than d blue. As the wavelength reduces, the focal spot diameter also reduces, because the diffraction is going to reduce with wavelength. Therefore, shorter is the wavelength, tighter will be the focusing. Focal spot diameter will be smaller. So the tight focusability in turn can make the beam so intense that it can vaporize an ablate material from its surface without going through the liquid phase, a process known as ablation. Okay, now before we come to that, you see, suppose the power of your beam is, this is diameter, focal spot diameter is D. This is D, diameter of the focal spot. And suppose the power of the beam is P. So intensity of this beam at the focal plane will be power per unit area. So area is, if D is the diameter, then the area of this focal spot into which area over which the beam has now been focused is pi into d square by 4. That is the area of the focal spot diameter. So it essentially becomes 4p by 4d square. So then intensity is inversely proportional to the square of the focal spot diameter. Now, so for shorter is the diameter, more would be the intensity. It goes as inverse, proportional as inverse square of the diameter square. So the intensity for blue beam is going to be much more than intensity of green, which will be much more than intensity of red. So by lowering the wavelength, you can increase the intensity at the focal plane. So what is the, how can we apply it? See, the tight focusability in turn can make the beam so intense, the intensity can be so high if you can reduce the wavelength. So intensity then basically is proportional to 1 by lambda square, because D is proportional to lambda. Higher is the lambda, more will be D. So by reducing the wavelength, you can increase the intensity to a very significant extent. And it can be so intense that it can vaporize an ablate material from its surface without going through the liquid phase. Directly it will go to vapor phase from the solid phase without going through liquid phase. Such a process is called ablation. So by ablation you can actually remove material from a material surface, and for that you need extremely high intensity, which you can produce by reducing the wavelength of the laser. But there is another very important point here. If you can increase the intensity, you can increase the intensity two ways. Either you increase the power. See, if you increase the power, then also intensity will increase. But if you increase the intensity by reducing the focal spot diameter, that means you make the focal spot smaller and smaller and increase the intensity. It has an advantage. What is the advantage? While the tiniest focal spot generates a well-defined microstructured surface, because if you reduce the focal spot diameter, then you will create micro hole. As you ablate material, you will create micro hole because your focal spot diameter is very small. By you are reducing the wavelength and making it smaller and smaller. So you can create micro hole through the process of ablation on material surface. Material removal through ablation keeps the process surface extremely clean with no tail, because everything is vaporized, ablated. Nothing will remain on top of the surface. So with no visible thermal effect. One action but two advantages. No thermal effect because it doesn't melt. The material doesn't melt. It doesn't go into liquid phase. It directly goes to vapor phase from the solid phase. So the surface on which you are creating such microstructure will remain absolutely clean and neat. So that means one action but two advantages. This has very important applications. What are the applications? It is not surprising that this behavior of light makes an ultraviolet laser. Ultraviolet laser is one which wavelength is very small, so that you can create very high intensity at the focal spot. Ultraviolet laser more suitable for microscale applications such as fabrication of advanced semiconductors, that is nano chips, nano integrated circuits. And there is a global race now to reduce the size of the chips, IC chips, which would eventually result in reduction of the various electronic devices, such as the mobile phone that you use. You have incredibly large number of operations that is possible from such a small device because of reduction of the chips, and for this you need ultraviolet laser. Then engraving of precision tools, marking of surfaces without changing its structure or chemical composition, and microsurgery. Essentially, one important application in microsurgery is LASIK eye surgery, where actually you use an ultraviolet laser and grind the cornea of your eye, basically to engrave the optometrist's prescription of eyeglass prescription, engrave it right onto your cornea. Cornea actually is 2/3 of eye's refractive power. So by grinding cornea, you can actually correct your vision, and you would not require to wear an eyeglass, because optometrist eyeglass prescription can be clearly engraved onto your eye. So you do this by using ultraviolet laser. You basically optically grind it, microscale grinding. All right, so that is why why ultraviolet laser capable of emitting coherent light at ultraviolet wavelength is important. Very important applications. Now, let us now see why Excimer laser is important. Obvious question is it difficult to build ultraviolet laser? Yes, indeed it is difficult. You see, with decreasing wavelength, it becomes progressively more difficult to build a laser. Why? This is because as the wavelength reduces, as the wavelength of the lasing transition reduces, the upper level, laser level, has to go up and up in energy. And as it happens, as a thumb rule, the spontaneous lifetime of this level continues to reduce. That means if you transfer population on that level, the energy would very quickly relax, will leak out due to spontaneous emission. It will be difficult to keep population stored in that level for a long time, or the realization of population inversion becomes difficult because spontaneous lifetime of the level reduces, so the energy will very quickly leak out of this level. Let us try to understand this in a little more detail. You see, let us consider a laser, typical laser, that is based on 4-level energy, that operates on the basis of 4-level energy scheme. So this is the ground level, which is characterized by energy E equal to E0. This is the lower laser level, E equal to E1. This is the upper laser level, and this is the pump level, which helps you to transfer population of the ground to the upper level. Now, in the beginning, all the population is residing in ground level. Other levels are empty. So you pump, say, atoms or molecules or whatever from here to the pump level. And from here, it quickly relaxes to the upper level. And so this is the lasing transition, which gives you the wavelength λ1. So if you have to reduce λ1, you will have to increase this gap That means you have to increase E2 minus E1. Then only the transition will give you shorter wavelength. Of course, you can appreciate this point. So how do you increase this gap? Two ways. Either you take this lower laser level down, or take the upper laser level up. Now, taking this lower laser level down is not so easy, because the room that over which you can take it down is limited, because ground level is fixed, zero energy level. And if you suppose you do it, and if you try to bring it closer to this, then Maxwell's Boltzmann distribution will ensure that this level then starts getting populated. Some of the ground population from the ground level would begin to appear here, because it is coming closer to the ground level, Boltzmann distribution. And this would tend to reduce the population inversion, which will hinder the operation. So this way, reducing the wavelength is not advisable. So the other option is take it up in the energy. So take both pump level and upper laser level up. So this is shown here. You have taken them up. They are going up. So the gap has increased, and now this transition is giving light at shorter wavelength compared to this. But then the problem that occurs is that as we are raising this level up in the energy, its spontaneous lifetime reduces. It becomes increasingly difficult to store energy here. Energy will leak out as a result of spontaneous emission. So that is why it is increasingly difficult to make a laser at shorter and shorter wavelength. In fact, the laser, as you know, was invented in 1960, and that operating wavelength was, I think, red, ruby laser, 600 some wavelength, 680 or something, nanometer, visible, red end of it. And yeah, and the first UV laser, that is argon laser or ionic laser, operated I think in 1965, after 5 years. But argon ion laser, as you know, or any ionic laser, has very small operating efficiency, 0.1% to 0.001%, very low efficiency. That is because the active medium here is ion. It is not neutral atom. So you have to consume a lot of energy in making these ions from the neutral atoms. We have of course studied this. That's why there are some gas lasers like ion lasers that are capable of emitting ultraviolet light, but they perform too feebly to serve any meaningful purpose. So they probably did not actually, that kind of application which we just mentioned, they were not a very good candidate for that. So the Excimer laser, which actually was the first real ultraviolet laser, it was operated sometime in 1970s. You see, more than 10 years after the invention of laser. So you can imagine how difficult it was to make ultraviolet laser. The difficulty arose from this, that as the energy level goes up in energy, its spontaneous lifetime reduces, so maintaining population inversion becomes increasingly difficult. Even if you consider the case of a vastly popular green laser pointer, let us consider. Although green is longer than ultraviolet wavelength, but it is still closer to ultraviolet than red. Even this green light does not originate directly from the lasing medium here. The laser is essentially an infrared laser, that is ND-YAG laser, which emits at 1064 nanometer wavelength. And then A fancy crystal is a non-linear crystal basically, is subsequently used to convert this infrared light 1064 nanometer into green light through a non-linear optical process known as second harmonic generation. That means it actually halves the frequency or halves the wavelength or doubles the frequency. That is called second harmonic generation. The ability of a rare gas atom to form a molecule only in the excited state made it possible to build an efficient ultraviolet laser. A gainful exploitation of this unique property of rare gas species to the development ultraviolet laser based on a transition between n equal to 2, n equal to 1 of this molecule, which invariably results in the emission of an ultraviolet wavelength. I think I will end here today, and next class I shall explain to you the underlying physics of operation of Excimer laser and show how Excimer laser actually helped realize the emission of coherent light from a laser at ultraviolet wavelength.